In section 5.3, we'll be analyzing trigonometric graphs for the sine and the cosine waves. First, defining what the sine and cosine waves represent in terms of our definitions of the trigonometric functions and the underlying geometry of the unit circle. And then applying transformations to those waves, the same transformations as we've seen previously in the course. Those would be shifts, reflections, stretches, and compressions. They will come with different names, those transformations, with context of the trigonometric waves. However, for example, the quantity which would cause a vertical reflection or a vertical shift or a vertical compression is represented in this equation here by the uppercase A. It might not always be an uppercase A. In this textbook, you might see lowercase a for that variable right there, or parameter. But here I like to write it using an uppercase A for consistency with my other work as well. So the stretching factor here, if we are considering how much it stretches or compresses the graph vertically, we're going to refer to that amount of stretch or compression as the amplitude of the wave. Now, the amplitude of a trigonometric wave can be thought of as the height of the wave from its equilibrium value to its to the peak of the wave, called the crest, or to the trough of the wave, okay, which is at the minimum. So the amplitude itself for a trigonometric wave, when it is defined, requires that we have a maximum and we have a minimum. There has to be a ceiling and there has to be a floor, which the sine waves and the cosine waves will have both of those. The other four trigonometric functions, which we'll take a look at briefly in section 5.4, the other trigonometric functions all have asymptotes, vertical asymptotes that is. So they will neither have a maximum nor a minimum, and hence will not have an amplitude defined. But the sine and the cosine waves will have a defined amplitude. Taken straight from the equation, the amplitude can be found as the absolute value or the magnitude of that quantity A. That extracts from the equation the information strictly about the distance measure, the height of the wave. To calculate the amplitude, let's say if we were looking at a wave, and here's what these waves are going to look like, by the way. Okay, we'll see why the waves have to look like this. Bobbing up and down, there's going to be a maximum. Maximum is found at the crest of the wave, keeps getting returned to. There's going to be a minimum, and the minimum gets returned to again and again at the trough of the wave. And then the balance between the two going right through the center. Okay, I call that equilibrium. Okay, in many contexts, we're going to refer to that as the equilibrium. Okay, so the amplitude is the height of the wave when taken from equilibrium to the crest. And by symmetry, that would exactly be equal to the depth of the wave, if you will, below equilibrium, okay, down to the minimum where the trough is. Okay, so one way to calculate the amplitude then is, if we know the maximum and know the minimum, we can take the difference between maximum and minimum and then divide that by 2, or 1/2 of the difference between the maximum and the minimum. Okay. But if we didn't know both the maximum and the minimum, maybe if we knew the maximum by looking at a graph, maybe if we knew what the maximum was and if we knew what the equilibrium was, we could also take the difference between those two quantities. That would be another way. Or if we knew the equilibrium and the minimum, we could take the difference between those two as well. That would equal the amplitude. Okay, this would always be a positive number, amplitude is. Okay. If A itself, back in the equation, if A was negative, however, that's actually going to cause a vertical reflection of the wave. It would be the difference between, let's say, a sine wave which is shaped like this versus a sine wave which instead would go like this. Okay, so both of these would be represented by sine waves, but here we would have an A value that is greater than 0, and here we would have an A value that is less than 0. Okay, and that's for the y is equal to, well, let me go over A in there, at least A times the sine of x, not dealing with any other quantities there. Okay. So if A is negative, we get a vertical reflection. The magnitude of A, however, tells us the amplitude of the wave. the period of the function, the period is defined as the length of time for a cycle to repeat. That is, for a pattern to repeat. It's not just the length of time until the y value returns, but it is until the entire cycle were to repeat. So if I were, for instance, to examine one complete wave here, let's say I go from this point right here, okay, until the entire cycle repeats, I would have to go out to here, right? Because then I could copy this image right here, this shape, and then paste it again, and I would get exactly the same pattern, and it would go again and again and again. That length, which looks here like a physical length, if this were taken over the time domain, if this were a length of time, then this is called the period. If this were a physical distance that we were measuring in terms of, let's say, meters or centimeters, or for example, we're going to call that distance instead a wavelength. But we're going to be modeling these as functions of time, and we're going to refer to this horizontal displacement as the period, therefore, the amount of time it takes for a complete cycle to end up repeating. So that can be the distance between a crest and a crest. That would be the period. It can be the distance between a trough and a next trough. That would be the period. But be careful, it's not the distance between equilibrium and equilibrium. In fact, because it matters the direction that you're traveling. You want to see the complete cycle repeating. In fact, if we started at equilibrium here, we would not want to finish the period at this equilibrium, right? We'd actually want to go through that to the next one, so that we're not only at equilibrium, but traveling in the downward direction again like we were at the start. Now we can take note right here, and we'll take a look further into this in a moment in more detail. If we wanted to describe this complete waveform, where this is just repeating and repeating and repeating and continuing forever, we didn't have to start at this point right here. We really could have started at any point that we wanted and gone through one complete cycle. Right? We could have, let's say I started at, for example, this point down here. If I wanted to start at this point down here and examine the behavior, the pattern, I could go until this point right here, and that again would be one complete period right there. And then we could copy that image and we can paste it here and paste it again here, and in the end we're going to get exactly the same wave, carrying all the same information, whether we had chosen this green cycle here or this orange cycle. There's more than one choice that we can make when describing a waveform of this type. We can choose either sine or cosine, and we can choose either where A is positive or A is negative. Notice that this green cycle right here would be described where we have a sine function where A is negative, because we have this shape right here. If we had selected instead to, let's say, start at maybe this point right here, if we had then gone through the complete cycle, we would have ended right here. It's all from the same wave, all the same information when we carry it out to infinity and negative infinity. But then this one wave here in purple would instead be described by a sine model where A happens to be positive. Right? So we have flexibility in which one we choose because of the repeating nature of these waves. And it depends on where we choose to start our observation and complete our observation of one complete cycle. So when we're given a graph, again, if we are given a graph, we can extract information from the graph to determine what the equation would have been that could have represented that graph. And we have more than one possible equation we could construct that could represent a particular waveform. Okay, so when we're given an equation, back to when we're given an equation, how do we construct the graph? Okay, we know what A tells us. What does B tell us here? So this B, okay, recall, since it's being multiplied by the input variable x in this case, or it could be the input variable t, or whatever input is, if we recall from transformations of basic graphs of functions, that's going to cause us to have a possibility of a horizontal reflection as a reflection over the y-axis. That would be if b happens to be negative. Okay. And also, if we could just consider the magnitude of b, if that magnitude is either greater than 1 or less than 1, then we're going to have a horizontal stretch or a horizontal compression. Okay. Within context of the trigonometric functions, the title we give to that, horizontal stretch or horizontal compression, that is the magnitude of b, that would be the frequency of the wave. That's how frequently the wave cycles are repeating in a standard period. So let's say, for example, I have a waveform, it maybe goes like that over a span of from the beginning to the end of this whole cycle. Let's say that is over a span of 2 pi in displacement. So a time displacement of 2 pi. Okay, just for simplicity. Well, if we count the waves that occurred in that span, that would be starting from the beginning. If we go, that would be 1 complete wave to there, 2 complete waves, 3 complete waves. We would count that there are 3 waves per 2 pi cycle. So we would have a frequency of 3 for this example right here. Okay, so the magnitude of B is telling us the count of the number of waves that we're going to see over a span of 2 pi, or whatever the standard period is for the wave. We're focusing in this section on only the sine and the cosine, and the sine and the cosine are going to have a standard period of 2 pi. The period in general for a sine or a cosine wave, that is when we're reading from the equation, we say, what is the period of our modulated function? The period can be found by taking 2 pi and dividing that by the magnitude of B. So, for example, then, if we had a frequency of 3 waves, that's if B was equal to either 3 or -3, then the period would be 2 pi over 3 for that example. Okay. Now, we would not want to choose a negative number here, because then we would be saying that the period was negative, right? 2 pi divided by -3 would give us a negative period. But that doesn't make sense, because period is supposed to be, well, it can be geometrically represented as a physical distance, the same as the amplitude can, but also we're interpreting period in terms of applications as the amount of time it takes for a cycle to repeat, and we're not going to measure time as a negative quantity. But we're going to have to deal with what if B happens to be negative. Okay, if B is negative, also, okay, I'll make a note again here that the magnitude of B is equal to the frequency of the wave. Okay, now if B happens to be a negative quantity, we can use the even or odd symmetry of the function, that is either the sine or the cosine function. Recall that sine is odd and cosine is even, okay, in order to deal with when we have a negative value of B. Okay, so I'll just say, all right, if B is less than 0, okay, then you can simplify the equation by using the even and odd symmetry. So we can take a look at an example like that. Okay, so we have, what if A is less than 0? Vertical reflection. What if B is less than 0? We could say there's a horizontal reflection, but in fact it's going to be more advantageous to us to instead use the even and odd symmetry to simplify the model instead. All right, phase shift and horizontal shift. Now the variable C in this equation here is called the phase for the function, or for the wave, the phase. Phase is not the same as phase shift. In fact, in our textbook and in certain resources, it will be called phase shift, what we're trying to find, but I'm going to refer to it as the horizontal shift. Because, again, I do not want to confuse phase with phase shift. Now, C is equal to the phase, but the phase shift or horizontal shift is, as we have studied already previously in the course, it is a horizontal translation of the curve, okay, from its standard position for the basic graph. Now, the horizontal shift I'm denoting with the variable h here, the same as we've seen previously in the course. Now, your textbook might use different variables here. It does use different variables in this Stewart textbook. But I'm going to stick with the horizontal shift with the variable h and the vertical shift with the variable k, because we've used h and k before. We used it with quadratic models, for example. I also used it in discussing transformations in general, and we used it as the center for a circle. So it seems to make sense to me, for consistency, to use the variable h to represent a horizontal shift. Again, the minus sign is because it's always in the opposite direction we would otherwise expect. And k is the vertical shift. Okay. Okay, but it's not uncommon. In fact, it's quite common to be given a sinusoidal wave, a sine or a cosine model, where it's written in this form, where you can have the quantity in the argument as bx plus c. We can factor out the value b from that. Factor out b, and you can rewrite it as b times the quantity x plus c over b. And then we can replace the positive, or the plus c over b, we can replace that with minus h. It's similar to what we would have done when we did completing the square type of a process, when we were solving for the vertex of a parabola after completing the square. Okay, it's another way of writing the model. When you're writing the argument in this form, bx plus c is the argument, okay, then c is called the phase. When you factor out the frequency quantity, the variable b, when you factor that out, okay, then you can rewrite it in this form where the argument is b times the quantity x minus h. Then h is the horizontal shift, or the phase shift of the wave. Okay, so they are not the same as each other. Okay, this I have written out here, typed out here in more detail down here. So you can solve formulaically for what the horizontal shift is. H is going to be negative c over b. Okay, for example, so that's because if you factor out b, again, you take out b from here, you're going to get x plus c over b. Well, if you set x plus c over b equal to x minus h and solve for h, you're going to get h equals negative c over b. So you can solve for the horizontal shift formulaically. But I'm going to show you another way in which you can find the horizontal shift, which again is also called the phase shift. In fact, let me change that. Okay, the phase shift is the horizontal shift, okay, denoted by the variable h in my design of the equation right here, and h can be formulaically calculated by taking negative c over b. The justification for that is if you factor out b from this argument, you'll get b times the quantity x plus c over b. Then x plus c over b would equal x minus h if h is equal to negative c over b, because x minus negative c over b is the same as x plus c over b. So there's your justification right there. So you can find the horizontal shift by using knowing the values of c and b by this, formulaically. I'm going to show you another way in which you can find the phase shift, also called the horizontal shift, however, and it's going to be by using the standard quarter points of a complete cycle, or what I refer to as the quarter points. The quarter points are 5 points that you can find on any complete waveform cycle, one complete period, okay, for a sine or a cosine wave. So I call them quarter points, and the reason there's 5 of them as well, if we refer back to the unit circle, all right, on the unit circle, where we were defining the trigonometric functions initially as the coordinates of a terminal point, right? We have the terminal point P of x, y. The coordinates x and y can be related to the input variable t, where t represents the distance we have traveled along the circular path starting from the point 1, 0. So for instance, t would equal 0 at this point right here, where the output for the x variable would be 1, so the cosine of 0 equals 1, and the output for the y variable would be 0, so the sine of 0 is equal to 0. Right? So I would call that the first quarter point. The first quarter point at the beginning of this complete period, this complete path around the circle, where t is equal to 0. The second quarter point would be found where t is equal to pi over 2. If t is equal to pi over 2, what is the associated y value and x value for this terminal point? That is, what is the associated sine of pi over 2 and cosine of pi over 2? The next quarter point would be found here. That's where t is equal to pi. Okay, so so we got quarter point 1, 2, and 3. Quarter point 4 would be found when t is equal to 3 pi over 2. And quarter point 5 would be found when we complete the cycle and get back, okay, and get back to the starting position again. So that would be a total of 5 quarter points on one complete cycle. Each quarter point is therefore going to be separated from the last one by a quarter of a period. If a period is equal to 2 pi, that is the amount of time it would take for us to complete one complete cycle. To go through this circle one time would take 2 pi, a period of 2 pi. Okay, then if we subdivide that into 4 quarters, okay, each then quarter point or quarter period is going to be separated in this most basic case by pi over 2, because 1/4 of 2 pi is pi over 2. So in general, okay, we're going to want to take whatever the period is for the transformed wave function, whatever the given period is. If we want to divide that period by 4 in order to find out what length of time there is for each quarter period. All of this is going to be, I'm going to show you how to do that by virtue of doing this. We're going to set the argument of the sine wave and the cosine wave, that is the bx plus c. No matter what b is and no matter what c is, this is going to work. You set bx plus c equal to the 5 quantities 0, pi over 2 pi, 3 pi over 2, and 2 pi. That is then to solve for x, which then in this case it will always be linear equations because x is to the first power. You'll be solving 5 linear equations, and that will give you the 5 x values for the quarter points. And that's always going to work. The x value for the first quarter point will always be equal to the phase shift. And that's how, instead of using this formula here, I would say, well, that's how you can find out what the phase shift is. By finding the 5 quarter points, you plot those 5 points on a coordinate grid, in the rectangular coordinate system, and then you connect them in a smooth wave, and that completes the cycle. In that wave, you can determine easily what is the phase shift because it's the x value at the first quarter point. Okay, and you've labeled all the important information. The y values will tell you what the amplitude is going to be. It's also going to tell you what the equilibrium is going to be as well. Equilibrium would be the value of k. All that can be determined by examining the graph. Okay, and the graph can be easily constructed by finding the 5 quarter points and connecting them in a nice smooth wave. Okay, also give you detailed information here about if you are given the graph of either a sine or a cosine wave, how can you figure out, right, the values of the parameters k, a, b, and c. First off, where k is equal to the equilibrium. Okay, the equilibrium, that's the central value that goes right through the center. Okay, it would go right through here, would be equilibrium. Okay, if you know the maximum and you know the minimum, you can take the average of maximum and minimum. The average of maximum and minimum, that's found by adding them and then dividing by 2. Well, that would have to be equilibrium. Okay? That's not the same as taking the difference between them. Remember, right? Take the difference between maximum and minimum and then divide by 2. You would get the amplitude of the wave instead. Okay? Now, if it's possible that the graph is given in such a way that the equilibrium is obvious. Maybe you already know what the y value is that goes right through the center, in which case that is the equilibrium or the vertical shift, and you're done. But if you didn't know what that central value was, and if you did know the maximum and the minimum, you could calculate what the equilibrium was, essentially by symmetry, because the equilibrium has to be halfway between maximum and minimum, for example. How do you calculate frequency when you're given a wave? Well, we said that the period, p, is calculated as 2 pi over the magnitude of b. Now, again, we dealt with if b was negative, will you be able to use even or odd symmetry to deal with that? So that's not going to be an issue here. When we're constructing the equation from the graph, we can always just select b to be positive. We'll be able to do that. And the way we find a value of b that would be sufficient would be by using this formula. So b then, or the magnitude of b, therefore, would be found by taking 2 pi divided by p, where p is the length of the wave. It is the period. Right? So if we know the horizontal displacement, okay, the horizontal length of the wave for one complete cycle, okay, that is the period when it's taken over the time domain, which it will be for us. Okay, so if you know what the period is, if you can read that from the graph, that is, if you know what the x value is here and the x value is here, okay, you can take the difference between those two, and that would be the period. Well, if you divide 2 pi by that period, you would be left with the frequency b. So that's how you can know what the value b is. All right, and I already mentioned the horizontal translation. Okay, if you find these values, a, b, and h, and of course k as well, that allows you then to write the wave function as either this or this. Okay, in one of these two forms. And if you're tasked with having to write it in this form or this form here, well, it's simple. Once we have it already written in this form where we already talked about how to find k, a, b, and h, you can just distribute b, and you would have this form instead, and be done with it. Okay, take a look at the instructions to any example whereby you're having to write the equation to see which form it is you're being asked to express it in. Okay, so let's take a look at why the graphs of the sine and the cosine are as they are. Okay, so we are, again, by definition, we've defined the trigonometric functions so that if there's a terminal point on the unit circle, the coordinates of that terminal point can be associated with the arc length distance, or the distance it took to get there from the standard point, from the initial point 1, 0. This is if we are in standard position. This can be related to a central angle of rotation that we call theta, and t is equal to theta. Okay, so we defined the trigonometric functions so that y, the y coordinate of this terminal point, is equal to the sine of t, which we can also say y is equal to the sine of theta, because t is equal to theta as long as theta is measured specifically in radians. Okay, and the x-coordinate of this terminal point would be the cosine of t or the cosine of theta. Okay, so it's the trigonometric functions are just names that are given to this relationship right now within this geometry. The coordinates versus the arc length, the distance, okay, to get to that terminal point when we are in standard position. So consider, if we just focus on the sine wave for right now, let's say I wanted to graph the function y equals the sine of t, for example. Okay, y equals the sine of t. That is, what is the y coordinate as the value of t seems to vary? Starting at the beginning here, where t is equal to 0, t is equal to 0 when we're at this point right here, t then increases, okay, at the end of quadrant 1, t would equal pi over 2. Along the way, the y-coordinate started at 0 until 1, right? The y-coordinate started here, and it moved up until it reached a peak of 1. Then what happened? As t continues towards pi, the y-coordinate, right? We're ignoring x completely right now. The y-coordinate, though, falls down back to 0 again. Right? So it returns back to 0. And then we continue with t approaching 3 pi over 2. Then the y-coordinate approaches negative 1. So this is going to go down, right, to negative 1. And then as t approaches 2 pi to complete one complete cycle, the y value is returning to 0 again. Okay, so imagine, if you will, imagine that there is a point or a particle that is an object that is rotating on this circle. And let's attach that now to a stylus, like a pen. Okay, and this thing is just rotating and rotating like this. Okay, as it's rotating, imagine taking the paper or the whiteboard behind it and shifting the whole whiteboard to the left as this thing is rotating. And then imagine the pattern that this is going to trace out. We're just going to see it bob up and down and up and down and up and down. And another way to visualize that in a physical sense is to imagine that from the ceiling, in whatever room you're in, imagine there is a spring hanging from the ceiling that has a weight attached to it, that has some mass. Okay. So some mass that is attached to a spring. If we were to pull the weight, okay, if we were to walk in to the room and this thing were just sitting idly by, if it were just sitting steady, then we would say that it's hanging at its equilibrium, right? Its equilibrium height. It's just hanging there, not moving. Okay, so it's just hanging where it naturally wants to hang at, okay, at the height that it wants to be at. If we were to then pull the weight down and release it, it would then start bobbing up and down and up and down and up and down, right? We could see that from here it's going to go up and then down and then up and then down. And this is not going to happen, it's not going to move outward like this. It's just going to go up, down, up, down, up, down, up, down. But if we were to move the whiteboard behind it and attach a stylus to this, it would trace out a wave pattern like this. Now, if we were to start collecting data, collecting position information for the weight, when it was at an equilibrium and it was starting to go up, okay, we would trace one complete cycle. If we were to trace one complete cycle, it goes up, and then it comes down, right, and then it goes up again, okay? That would exactly be in the shape of a sine wave, the standard sine wave, the same wave that we just talked about from here, with a particle moving around in a circle. It's just going to keep repeating. And if this, if the height of this wave is not changing, if this is going to maintain a constant height outward for forever, we call that harmonic motion. Simple harmonic motion is what that's called. If there are external forces, however, that are acting on this, that are going to cause this displacement, this vertical displacement, to change over time, like if it were to get, if it in fact were to get smaller and smaller, like under like a shock absorber or something like that, eventually to balancing out, that would be called damped harmonic motion. Okay. We're not considering damping right now. I just want to consider simple harmonic motion. This is just going up and down, and let's imagine that it goes like that for forever. Okay? If we start our observation of this waveform from here, from equilibrium as we move upwards, okay? Upwards towards a crest, which is found at the maximum. Okay? And then it goes back down to a trough, which is found at the minimum at the trough, in other words, and then back to equilibrium again to then repeat the cycle. So the actual physical weight, right? So it would go up and then down and then back up again, and then it's just going to repeat that behavior. Okay? This particular choice that we have made here would be the standard sine wave. Right? So it starts where the y coordinate of the terminal point was 0 when the input t was equal to 0. So it starts at the point 0, 0. And then it moves up to where we have when t is equal to, let's say, pi over 2, right, at the end of the first quarter of a complete cycle, or the first quarter period. Okay, when t is equal to pi over 2, the y-coordinate is now 1. So this nice and smoothly and continuously approaches that point right there. Okay, and along the way, we go through values of t that we've seen before, pi over 6, pi over 4, pi over 3, and the associated y-coordinates for that as well we know to be 1/2 root 2 over 2 and root 3 over 2. So this is increasing towards 1. And then as t passes pi over 2 and goes towards pi, okay, the y-coordinate is then going to return back to 0 again. That's back at equilibrium. All right, so here we have the maximum is equal to 1. Then as t goes to 3 pi over 2, the next interesting value of t at the end of the third quadrant, so this would be quarter point 1, 2, 3, 4. Now I'm going on to quarter point 4. When t is equal to 3 pi over 2, the y-coordinate is now -1. So now we're down here, and nice, smooth, continuous curve comes down to there. And then as t goes to 2 pi, the y-coordinate is returning back to 0 again, back to equilibrium. So t is equal to 2 pi. The y value for the terminal point is 0. Here's our wave. This is for one complete cycle. Now, after that one complete cycle, what's going to happen is the entire pattern is going to repeat again. Okay, and it's just going to repeat again and again and again. Okay, in both directions, it would repeat again and again and again. If this is simple harmonic motion, right? No damping here. It's just going to continue. All right. So this is the graph of y equals the sine of t. Now, in order to examine y equals the cosine of t, we would just consider the relationship between the x coordinate of the terminal point and the input variable t instead. So what would that look like? Y equals the cosine of t, okay, versus t. Okay, So I'm using y as the output here, but we could think of it as x right here. They're interchangeable, whatever variable you want to use to represent it. In the unit circle here, I want to use x because it's the x-coordinate of the terminal point. Okay, notice that, for instance, when t is equal to 0, the x-coordinate is 1. So we already have the initial point. And where t is equal to 0, the value of cosine would already be 1, because it is the x-coordinate of the terminal point. So it starts here. Okay. Now what happens as t approaches pi over 2, as we move through the first quadrant? The x-coordinate is approaching 0. So when t equals pi over 2, x is equal to 0. That means the cosine of pi over 2 is equal to 0. Okay. So again, when we get to where t is equal to pi over 2, the cosine of pi over 2 would be 0. It would be the x-coordinate of the terminal point. And this is nice and smoothly and continuously going to approach that value right there. Now, as t approaches pi, the x-coordinate goes to -1. Okay. So now t is approaching pi, and the x-coordinate of the terminal point, which is therefore the output of the cosine, would be -1. So this is nice, smoothly, and continuously going to approach that quantity right there. What happens as t approaches 3 pi over 2? The x-coordinate is going back to 0 again, back to equilibrium. So we're here. And as t approaches 2 pi, well, we're going to get back to the beginning of the cycle again. When t is getting to 2 pi, the x-coordinate here is 1. So the cosine of 2 pi is equal to 1. So we're going to complete the cycle and get back to the maximum again. And then the entire pattern is going to repeat. So we can copy this image and we can paste another one right next to it, and we can continue to paste again and again and again outward towards infinity if we wish. We'll try and get a decent graph, right? Something like all right, let's say something like that, right? More or less. Okay, it's just going to continue to repeat in both directions. Well, you notice that, maybe you will notice, if you extend, or if you compare these two waves to each other, if you were to just ignore the axes entirely, right? If you were to just erase the x-axis and y-axis, the t-axis and the y-axis in both of these cases, these two waves, in fact, are analytically the same wave as each other. Right? What is it that's the same about them in terms of their features, and what is it that's different about them? First off, what is the amplitude? The amplitudes of both of our waves, okay, let's do this in, let's go blue right here maybe. Right? The amplitudes for both of our waves, that is the height of a wave, right, from equilibrium to maximum, for example, and by symmetry also from equilibrium to the minimum. The amplitude is equal to 1. It's the same for both of these. Right? The period of each wave is equal to 2 pi. That's the length of one wave. Okay, one complete cycle is exactly equal to 2 pi. Okay? And therefore, the value of b, the value of the frequency, was equal to 1. We have one complete wave within a span of 2 pi. Okay? The value of the equilibrium, k, that's right through the center, okay, k is equal to 0. In both cases, k is equal to 0. Okay. And what about the horizontal shift? The horizontal shift, well, these are the standard waves, and the standard waves are not shifted at all. But how about relative to each other? Okay, relative to each other. We'll use red. Okay, so notice y equals sine t and y equals cosine t, okay, are the same graph, but they are horizontal shifts of each other. By how much? All right, so for instance, if we took the sine wave right here, if we were to shift it over this way, shift it to the left until this point at the maximum merged with the y-axis, notice that that would give us the cosine wave instead. Similarly, if we took the cosine wave and we shifted it to the right until the maximum was above pi over 2, we would have the sine wave instead. Right? So they are shifts of each other, okay, by pi over 2. Horizontal shifts of each other by pi over 2. So the horizontal shift is, well, relative to each other. Okay, if we have a sine wave, that is, if we graph a wave that has the shape of this curve, just the black cycle right here that starts at equilibrium and goes up, if we graph a sine wave, but if it doesn't start at 0, 0, if it starts somewhere else, either to the right or to the left, then wherever that starting point is, okay, its x-coordinate would be therefore the horizontal shift relative to a standard sine wave. Similarly, if we were to graph one complete cosine wave, that is from maximum to maximum of one of these waves, okay, whatever the x-coordinate is for the first point, called the first quarter point, or what I'm calling the first quarter point, whatever the x-coordinate is of that first quarter point would be considered to be the horizontal shift of the standard cosine wave. Any wave pattern that we have can be expressed as either a sine wave or a cosine wave. All right, let's take a waveform that is simple harmonic motion, so no damping here. Let me try that again. All right, no damping here. Okay, if we were to model this wave, let's say, again, if we were to model it from equilibrium back to equilibrium again, where we are moving upward, for example, from here through one complete cycle to here, okay, I would describe that with a sine model. Okay. Describe it with a sine model whereby the value of A, which causes vertical reflections, the value of A here would be positive because it's going in that direction. A vertical reflection of this, okay, vertical reflection of this where A is less than 0 would also start at equilibrium. Would also start at equilibrium, but would start by going downward. So for instance, if we went from here at equilibrium and we went down towards the minimum and then we returned around back to an equilibrium after reaching a maximum, this cycle right here would be described also by a sine wave, most appropriately with a sine wave. We have the option of choosing a cosine wave, but if I were graphing this cycle, I would choose a sine wave where A was chosen to be less than 0. Notice that in both cases, though, okay, these are going to have the same value for P, the same period, the same frequency, okay, as well, okay, but they're not going to have necessarily the same horizontal shift. If the origin, let's say this was the origin right here. If this was the origin right here, then this wave would have a horizontal shift of 0, but this wave would have had a horizontal shift of however far this is from 0, right? Even though it's entirely the same wave and it carries all the same information. Now let's say we looked at a cosine model instead. We could model this whole wave with a cosine model. Okay, so let me extend this outward a little bit more. Okay, if we were to start our observation of this thing, it's bobbing up and down, and if we started our observation when this thing was at a maximum, and then we looked at its behavior until it reached a maximum again, I would describe that one wave right there with a cosine model. And that would be the cosine model like the standard cosine model is, where the value of A would be greater than 0. And finally, let's say purple here. Okay, so if we were to start our observation of this from a minimum then, okay, should I extend out a little bit further then, okay, if this were to continue on like this. If we were to start our observation from a minimum and allow this to go through one complete wave until we reach another minimum again, I would describe that also with a cosine model, but through virtue of a vertical reflection. So there A would be less than 0. Okay, and again at this stage I want to emphasize that all 4 of these choices can be correct as long as we choose the appropriate values for K, A, B, and C for the model that we choose. They all describe the same wave. Okay, when we're looking at a graph, we can determine whether we want a sine or a cosine, for example, by virtue of Do we start at an equilibrium, or do we start at a maximum or a minimum? Right? If we start at equilibrium, we should choose a sine wave. Do we have to? No, we don't have to. You can choose a cosine wave if you want to. The most natural choice when we're starting at equilibrium is to choose a sine wave, because the standard sine wave starts at equilibrium. And if we started at a maximum or a minimum for whatever cycle it is we're choosing to examine in detail, whatever initial period we're looking at, if we're starting at a maximum or minimum, the natural choice would be the cosine. Okay, and again, these are going to have also the same period and the same frequency as each other. In fact, they all do. Right? All four of these have the same period and they have the same frequency as well. Okay, so let's try out some examples then. Okay, starting with given an equation, construct a graph. So example 1. Okay, let's name some characteristics. State the amplitude, the period, and the phase shift. Then also graph one complete cycle, and for accuracy on the graph, label the 5 quarter points for the cycle. And we'll start with this one. F of x is equal to 3 minus 2 times the sine of x minus pi over 3, for example. Okay. All right, so we're given a sine model. So the form that we have, y equals k plus a times the sine of the quantity bx plus c. All right, or we can look at it in the form k plus a times the sine of b times x minus h if we wish. So we'll note, what is the amplitude? Okay, the amplitude is equal to the absolute value of a. That would be the absolute value of negative 2 in this case, so the amplitude is equal to 2. Okay, the period is equal to 2 pi divided by the magnitude of b. That's 2 pi divided by what is b? b in this case is equal to 1. Right? So 2 pi over 1, so the period of our wave is going to be 2 pi. And then the horizontal shift. What is a horizontal shift? We can find the x-coordinate at the first quarter point in order to determine that. Or you can do negative c over b, or you can look at it in this form. It looks like in this case, h is going to be, because this is already written as x minus a number, pi over 3, it looks like h is just going to be positive pi over 3. Okay, so I expect pi over 3 to be the x-coordinate at the first quarter point. Okay, now the shape of this wave right here, notice we have the value of a is negative 2, a is less than 0. So we have a value of a that is less than 0, and we're dealing with a sine wave. We have a sine wave. A is less than 0, and that means we expect a cycle to start at equilibrium and move down towards a minimum. This is the shape that I expect our one complete wave to take. Starting at equilibrium, going down towards a minimum, back to equilibrium, up to the maximum, and back to equilibrium again for 1, 2, 3, 4, 5 quarter points that it'll go through. If we can find those 5 quarter points, okay, we can find those 5 quarter points right now, then we can connect them in a nice smooth curve. So that's what I'm going to do, and that's what's going to give us a nice graph. Find the quarter points. How do you find the quarter points? You said bx plus c. Put that down here. Bx plus c equal to the set of quantities 0, pi over 2, pi, 3 pi over 2, 2 pi. What is bx plus c in this case? In this case, it's x minus pi over 3. That's what it is. X minus pi over 3. All right, so x minus pi over 3 equals 0. X minus pi over 3 equals pi over 2. x minus pi over 3 is equal to pi. X minus pi over 3 is equal to 3 pi over 2. And x minus pi over 3 is equal to 2 pi. Note, you now have a set of 5 linear equations. So these are not that difficult to solve. These will always be linear equations, no matter what b and c are equal to, because x is always to the first power. And we can solve these by adding pi over 3 to the other side in this case. So x equals pi over 3, okay, that is the x coordinate at quarter point 1. We still need a y coordinate. Notice that this also means that the value of h is equal to pi over 3, because this is the x coordinate at quarter point 1. We'll see that from the graph. Okay. Now the second quarter point is located where x is equal to pi over 2 plus pi over 3 with a common denominator of 6. That gives us 3 pi over 6 plus 2 pi over 6. That gives us 5 pi over 6. So that's our second quarter point will be located at that x value. We still need to figure out the y value. I'll give you a hint here. We already know what the y value is going to be because we can determine what the equilibrium is, and we already know what the amplitude is, right? Equilibrium is at 3. Right? We already know the equilibrium, the vertical shift, that's going to put us at 3, and the amplitude is 2, so the maximum would therefore have to be 2 above 3, and the minimum would have to be 2 below 3. These are going to be the y coordinates then for all 5 of our quarter points, right? We're going to be at the equilibrium for 3 instances, we'll be at the minimum once, and we'll be at the maximum once because we're on a sine wave. All right. The third quarter point is found where x is equal to pi plus pi over 3. That means we are at 4 pi over 3. Okay. The x coordinate at the fourth quarter point is found where x is 3 pi over 2 plus pi over 3. Okay, common denominator of 6. 9 pi over 6 plus 2 pi over 6. That gives us 11 pi over 6, just less than 2 pi. 2 pi would be 12 pi over 6. And then x equals, for quarter point 5, found where x is equal to 2 pi plus pi over 3. That's 6 pi over 3 plus pi over 3, which is equal to 7 pi over 3. So I want to label these 5 x coordinates on my axes so that I can graph this wave. All right, so I have the x-axis here. So I'm going to start this cycle at pi over 3. Okay. And the last x value in the cycle is found at 7 pi over 3. I'll put that right here. What does that mean that the period was, by the way? Right? The period would be from the start to the finish. The period would therefore be 7 pi over 3 minus pi over 3, which is 6 pi over 3, or 2 pi. We had already established that from the start that the period was 2 pi. We could see that we were given a frequency of 1. So pi over 3 to 7 pi over 3, and then that gets subdivided into equal-sized subintervals. First, we cut it in half, and then cut each of those subintervals in half again. Right? So we're going to have 1, 2, 3, 4, 5 x values labeled for this one complete cycle. Pi over 3 is at the start, and then we have 5 pi over 6, and then we have 4 pi over 3, and then 11 pi over 6, and finally 7 pi over 3. All of these x values are separated by a quarter of a period. What is a quarter of a period in this case? 1/4 of 2 pi, which is equal to pi over 2. That's how far apart these are from each other. For instance, pi over 3 plus pi over 2 would get 5 pi over 6. 5 pi over 6 plus pi over 2 will give you 4 pi over 3. 4 pi over 3 plus pi over 2 would give you 11 pi over 6, and so on and so forth. They're each separated by a quarter of whatever the period happened to be for the function we're analyzing. Now, what about the y coordinates again? Well, we have this is our wave, right? Really what we can do is we can find f of each of these quarter point values. For instance, what is f of pi over 3? Right? What is f of pi over 3 for our function right now? All right, where the function was 3 minus 2 times the sine of x minus pi over 3. Right? 3 minus 2 times the sine of x minus pi over 3. So pi over 3 minus pi over 3. Calculate that, we get 3 minus 2 times 0, because the sine of 0 is 0. Well, that just equals 3. In other words, we start at equilibrium, right? We start where the y value is equal to 3. 1, 2, 3, 4, 5. At pi over 3, we're starting at 3. Okay? What's going to happen if we plug 5 pi over 6 into there? We can plug 5 pi over 6 into the function, and we can calculate it. Okay, but I'm only going to do it for this one extra, for this one more output right here. Okay, because again, I'm going to say that we already know that the next point should show up at a minimum. Okay, and what was that minimum value? We predicted that this was going to go down to a minimum equal to 1 because the amplitude of the wave was 2. So we have 5 pi over 6 minus pi over 3. Okay, 3 minus 2 times the sine of, what is this? 5 pi over 6 minus pi over 3. Common denominator gives us 2 pi over 6. So 5 pi over 6 minus 2 pi over 6 is 3 pi over 6. And 3 pi over 6 reduces to pi over 2. The sine of pi over 2 is 1, and 3 minus 2 is equal to 1. So the y-coordinate for 5 pi over 6 is equal to 1. Okay, and I'll go off to green. So we started at equilibrium, we went down to a minimum. Okay, we're going to return back to equilibrium again. That's here at 3. And then the next quarter point is going to be found at the maximum. That would be up at 5. You can check by plugging 11 pi over 6 directly into the function and seeing that the output will be 5. And then 7 pi over 3 at the end of the complete cycle would put us back at equilibrium again. And I will connect this in a nice smooth wave. Okay, and there's our function graphed. Okay, this is a sine wave. The value of a was less than 0, so we had the shape like this for our cycle that we graphed. The horizontal shift, or the phase shift, okay, the phase shift was equal to pi over 3. It's how far the first quarter point is from the y-axis. It is, in other words, what is the x-coordinate, okay, the x-coordinate at quarter point 1. Okay, this was quarter point 1 right here. Okay, I can see its coordinates because I labeled the axes with exact values. I know that it's located at pi over 3, 3. This is quarter point 2 right here. This would be quarter point 3. Right, this is quarter point 4, and this is quarter point 5. Now, if we wanted to extend this outward in both directions, we could continue this waveform out. Right? You know, it's going to continue and repeat. Okay, so, all right. Let's see. If we subtracted pi over 2 from pi over 3, that's what 2 pi over 6 minus 3 pi over 6 is negative pi over 6. So by the time I get to negative pi over 6, then I would be at a maximum of 5. So this is going to kind of curve around like that. Okay, it's not going to max out at the y-axis. It's actually going to max out at negative pi over 6. All right, well, you know, more or less. Okay, right? So this is like negative pi over 6 right here. For example, that's where the next maximum would be. Okay, so we graphed the one complete cycle here in green. We didn't have to choose this as the cycle. We could have done any cycle we wanted. But if I want the quarter points, then I want to have, essentially you want to make sure the y coordinates of your quarter points are all going to be at either an equilibrium, a maximum, or a minimum. So if, for instance, if you had plugged in x is equal to 0, if you had started the cycle here, that would not count as a quarter point. That is neither happening at the beginning nor the end of any one of the 4 quadrants we would have had in the unit circle, for example. Okay, so it's not just graphing from like 0 to 2 pi. To find the quarter points, you take whatever the argument is, if it's bx plus c or if it's b times x minus h, either one, because they're the same thing. You take the argument of the trig function and you set it equal to the 5 values 0, pi over 2 pi, 3 pi over 2, and 2 pi. Solve those 5 linear equations for x, and those will be the 5 x coordinates of the quarter points. You can find the y coordinates by either plugging those x's back into the function to find out what y is, or analytically by saying what is the shape of this wave. If it's a sine wave, it has to start at equilibrium, and if a is a positive number, then it starts by going up towards a maximum. But if a is a negative number, it would start by going down towards a minimum. If it were a cosine wave, then it would have to start at either a maximum or a minimum, which is then determined by whether a is positive or negative as well. Let's take a look at a cosine wave now. Okay. So same instructions. Okay, let's state the amplitude, the period, and the phase shift. Okay, and then graph one complete cycle, label the quarter points. Okay, how about f of x is equal to the cosine of 3x plus pi over 2, for example. Okay. Now, let's see, what's the amplitude? The amplitude would be the magnitude of a. Well, let's see, what is a actually in this case, right? We did it in the last example also. We said that the form of the function we have here is k plus a times the cosine of bx plus c. We can rewrite that as k plus a times the cosine of b times x minus h by factoring out b if we wish. Okay, but the value of a from here is taken to be, well, 1, right? The leading coefficient of the cosine. Okay. Should we make it more interesting than that? All right, how about we make this value 1/2? Okay, we'll do that. All right, let's make the amplitude of this wave, therefore, 1/2. The value of a is taken to be 1/2. The amplitude of the wave is the absolute value of a, and the absolute value of 1/2 is 1/2. Okay, so that's that. K is equal to 0. That would be our equilibrium. Okay, and then b, the frequency, if b is positive, which it is in this case, b is equal to 3, so the frequency is actually 3 as well. If b were negative, we would use the fact that cosine is an even function. We'll take a look at the next example, how to treat that. And finally, c, the phase, is equal to pi over 2. That is not the same as the phase shift. We're going to have to figure out what the phase shift is. Now, the amplitude is equal to 1/2, so we have that. Okay, it's the absolute value of a. The period is equal to 2 pi over the magnitude of b. That's 2 pi divided by 3. So the period of our wave is 2 pi over 3. And the horizontal shift? Well, the horizontal shift can be found by calculating negative c over b, or we can find the x coordinate at quarter point 1. Okay, your choice, either way. Okay. We can factor out the b, okay, and that's going to give us the value of h as well. I'm going to go ahead, because we're going to have to graph it anyway, I'm going to go ahead and find the quarter points. I'm also going to make a note of what is the basic shape I expect to see. We have a cosine model, cosine wave, and we have a value of a that is greater than 0, is given to be positive 1/2. So the wave I expect to graph here as a complete cycle will start at a maximum and end at a maximum. And it's going to go through the equilibrium at 2 points, and it's going to hit the minimum at 1 point. And those are going to be the locations of the 5 quarter points for this cycle. If we were given, everything else is the same, but if we were given a negative 1/2 at the start, then a would have been negative. And in that case, then the shape would have been, if a was negative, we would have started at a minimum and gone up and then down again. And we would have had these as the 5 quarter points instead. All right, just by the fact that a would have been negative. Notice the amplitude still would have come out to be positive if that were the case. Okay, so those are some of the possibilities we would have. And of course, if we extended this wave outward, if it just continued to repeat and repeat, we would have seen that we could have found another cycle where we could have described it instead by using a cosine model where a was negative instead. Okay. All right, so that's the shape we expect. Where are those 5 quarter points going to be located? We take bx plus c, which is 3x plus pi over 2, and we set it equal to those 5 quantities. Okay, we want bx plus c is equal to the set of values 0, pi over 2, pi, 3 pi over 2, 2 pi. So that gives us 5 linear equations. Bx plus c is 3x plus pi over 2. 3x plus pi over 2 is equal to 0. 3x plus pi over 2 is equal to pi over 2. 3x plus pi over 2 is equal to pi. 3x plus pi over 2 is equal to 3 pi over 2. And 3x plus pi over 2 is equal to 2 pi. we have a set of 5 equations. What form are they? They are all linear equations, right? We have x to the power of 1 in all cases, so they're not that hard to solve. In all cases, the algorithm for solving is subtract pi over 2 and then multiply by 1/3, right? So you get, for instance, 3x is equal to negative pi over 2, and then multiply by 1/3, x is equal to negative pi over 6, for example, right? That's quarter point 1. That's the x coordinate at quarter point 1. Therefore, that's also the value of h. So we now have the horizontal shift. H is equal to negative pi over 6. If you want, you can check with this formula, negative c over b, if you wish, right? What was c? C was pi over 2. So negative pi over 2 divided by b was equal to 3. Negative pi over 2 divided by 3 is the same as negative pi over 2 times 1/3, and that is going to equal negative pi over 6. It's the exact same value that we could have found it formulaically. It's always going to be the x coordinate at quarter point 1 when you follow my strategy. Okay, 3x plus pi over 2 is equal to pi over 2. Subtract pi over 2 from both sides, you get 3x is equal to 0. Multiply by 1/3, you get x is equal to 0 then. So quarter point 2 is located where x is equal to 0. And of course, by looking at the shape of the curve, quarter point 2 is going to be located at an equilibrium, right? An equilibrium value. Where's equilibrium? 0 in this case is where equilibrium is. It's the vertical shift. Now we have 3x plus pi over 2 equals pi. Subtract pi over 2 from pi, we get pi over 2. Multiply by 1/3, x is equal to then pi over 6. Here we go. 3x plus pi over 2 is equal to 3 pi over 2. Subtract pi over 2 from both sides, we get 3x is equal to pi. Now multiply by 1/3, therefore x is equal to pi over 3. So quarter point 4 located where x is equal to pi over 3. 3x plus pi over 2 equals 2 pi. Subtract pi over 2 from both sides, we get 3x is equal to 3 pi over 2. Multiply by 1/3, then we get x is equal to pi over 2. And that's the x value for quarter point 5. Now we can set up the axes, and I can start labeling these where the x values are going to be for our one complete cycle. Y-axis, x-axis. Okay, so I'm going to start at negative pi over 6 and then go to pi over 2. Okay, so we have, if this is negative pi over 6 right here, we also have included 0 as well. Okay, then by symmetry we should go to pi over 6 on the other side. Okay, there we go. And then we have pi over 3. And finally we are at pi over 2. Okay, there's not a point right there, right? That's just where the x value is. Okay. Well, I haven't established whether there's a point there. I'll plot this in green. Now the y coordinates, okay, the y coordinates. Well, equilibrium, or should we do this in red? Equilibrium right through the center is going to be 0 because k is equal to 0, the vertical shift. The maximum, right, the maximum for our wave would be higher than equilibrium by an amount equal to the amplitude, and the amplitude is 1/2. So the maximum is going to be found at 1/2. The minimum would be below equilibrium, also by the amount equal to the amplitude. So the minimum is at negative 1/2. So it's exactly the height of the wave below equilibrium. So those are our y values. We're going to go as high as 1/2, as low as negative 1/2, and 0 is of course right in the center. Okay, so I'll label that we have 1/2 up here, and I'll label that we have negative 1/2 as well. Okay, so I expect the wave, again, because A was positive and we're dealing with a cosine model, I expect the wave to start at a maximum and then return to a maximum. Okay, so I expect the first point is going to be found negative pi over 6 and positive 1/2. I expect it to be located there. Then I expect it to continue down, okay, and return back to a maximum again at the end of this complete cycle. So it's going to have to cross through an equilibrium, that would be right here. It'll cross back through equilibrium here, and it'll be at a minimum right here at the center of that cycle. And I'll try to graph this as a smooth wave, not as lines so much as I want it to look like a wave. Okay, so give it a little bit of a curvature there. All right, and then that pattern can then repeat after that. Okay, we should be able to repeat it, and we would be able to find quarter points on that cycle as well, and we'd be able to find quarter points on this cycle as well, as much as we would want. But we're focused on this one complete wave right here. Now, what would be the period for our wave? That would be from this x value here, the beginning of the cycle, to this x value here. Okay, that's the period. And the period from our graph here, we see we can calculate as the difference between these x values. That would be pi over 2 minus negative pi over 6, right? The difference between those two. And that equals what? Pi over 2 plus pi over 6, which is 3 pi over 6 plus pi over 6 is 4 pi over 6, and that reduces to 2 pi over 3. So the period is 2 pi over 3, and that matches what we said the period was going to be from the start as well. Okay, so the graph and the equation are agreeing with each other as they always should. Now, just to be sure, when we plug negative pi over 6 into the function, we expect the output to be 1/2, right? Well, let's evaluate. F of negative pi over 6 equals, let's just see that it comes out to 1/2 like we predicted. The function is 1/2 cosine 3x plus pi over 2. So we have 1/2 cosine 3 times our x value, which is negative pi over 6, plus pi over 2. So this is 1/2 times the cosine of, well, this is negative 3 pi over 6, which equals negative pi over 2, plus pi over 2, that equals 0, and the cosine of 0 is equal to 1. So 1/2 times 1, which is equal to 1/2. So confirmed, yes. Let's say we did this for one other point. How about this one right here, where pi over 3 is plugged in? Just for example, what is f of pi over 3? We expect it's going to equal 0, back at equilibrium. Let's check. F of pi over 3 would be 1/2 times the cosine of 3 times pi over 3 plus pi over 2. Okay, and that's equal to 1/2 times the cosine of pi plus pi over 2, which is 3 pi over 2. Remember from the unit circle at 3 pi over 2, and that's the input, the value of the x coordinate would be 0, so the cosine of 3 pi over 2 is 0. This is 1/2 times 0, which is equal to 0. So pi over 3, 0 would be a point that shows up on the curve, and we have that point right here. So we have our 5 quarter points. Here's quarter point 1. Again, I can tell what the x value and y value are because I've labeled the axes with exact values. If these are not labeled, then I'm not going to know where your quarter points are. So please label your graphs accordingly. Either label this with an xy pair, or off to the side you can write down the coordinates of each quarter point clearly so I know what you're saying is what. Or you can label the axes exactly as I've done here. Here's quarter point 1 for our cycle. Here's quarter point 2 right here. Here's quarter point 3. Here would be quarter point 4, and here's quarter point 5. So we've done everything that we were asked to do. Amplitude, period, and phase shift, which can also be called horizontal shift. Okay, we found those, and we graphed one complete cycle with the 5 quarter points labeled for that complete cycle. All right, so let's now take a look at one more equation whereby we deal with what if b is negative. If b is less than 0, then what you can do is use even or odd symmetry to start the process, and then you can continue on and do everything that we've already just done. So for example, okay, let's say consider f of x is equal to the cosine of pi over 2 minus x, and let's say we wanted to graph something like that. Okay, notice that if we wanted to write this in the form f of x is equal to k plus a times the cosine of bx plus c, we would have to switch the order of the terms in the argument because we're saying that the x term comes before the constant term. So if we were to rewrite this, then in this form, we should write it as cosine of negative x plus pi over 2. And let's take a closer look at this then. Okay, here we have, okay, k is equal to 0, a is equal to 1, Okay, but b right now is equal to -1, and that's less than 0. C right now, C right now is equal to pi over 2. Okay, if we write it in this form. Now, let's note that cosine is an even function. We have f of x is equal to the cosine of -x plus pi over 2. And we'll recall that cosine is even. What does it mean when a function is even? Symbolically, it means that f of -x is equal to f of x symbolically. So for instance, for cosine, the cosine of -x is equal to the cosine of x. But it just doesn't happen to the x, it happens to the entire argument. If the entire argument is negative, you can switch it to a positive instead. So in order to say that the entire argument is in fact negative, let's factor out the negative. Take out a -1 from this argument, and that leaves us with an x minus pi over 2. Right, so now we have the cosine of negative, right? You could think of this as the cosine of negative t, where t is equal to x minus pi over 2, right? This entire argument is now has a negative that has been factored out of it. And since this is even, then this means that we can squash the negative and just switch it to a positive. So our function can be rewritten as the cosine of x minus pi over 2, therefore. And then we can continue with our analysis of this function by graphing this instead of the original one. Because cosine was even, we were able to change the sign of the argument. Notice that that didn't mean that we only changed the x from negative to positive. We actually had to change the pi over 2 from a positive to a negative. Both of them had to switch their signs. And then we can continue by graphing this, for instance. Right? We have a cosine model where a is positive. Now notice c is in fact equal to pi over 2 by this change, and now b is equal to 1. So we've changed b and we've changed c by using this symmetry. And if we graph this and then extend it outward in both directions to infinity and negative infinity, again, we're going to get exactly the same graph in the end as we would have had from this. Where it differs is the cycle that we're going to look at. Okay. The individual cycle that we're going to graph, okay, would have different quarter points, would start and end at different points. Okay, but if we were to extend it in both directions, right, they would end up overlapping each other as the exact same wave. Okay, so this graph right here, right, for instance, is a cosine model. It's positive value of a. It's going to look like, it's going to start from a maximum. It's going to end at a maximum. Okay, the equilibrium is 0. The amplitude is 1, right? So the equilibrium is 0. The maximum is going to be 1. The minimum is going to be -1. The value of x at quarter point 1 is going to be pi over 2, because x minus pi over 2 is equal to 0 would require that x is equal to pi over 2. So I expect that pi over 2, okay, to be at the maximum, and the maximum is 1. And then this thing is going to graph like a cosine wave, like that, okay. All right, it's going to get down to -1. Okay, here's the 5 quarter points, and we can find where those are. The period of this wave right here is equal to 2 pi over 1, which is 2 pi. Okay, so that means every quarter of a period, okay, every quarter of a period would be pi over 2, because 1/4 of 2 pi is pi over 2. So this would be an x value of pi. This would have an x value of 3 pi over 2. This would have an x value of 2 pi, and this one has an x value of 5 pi over 2, for example. And so there's our wave. And if we repeat this in both directions again, we're going to get, we're going to get the, the complete wave that we would have had anyway if we had graphed this and extended it outwards as well. Okay, so the horizontal shift here was pi over 2. It's the x coordinate of quarter point 1. If we were to continue this wave though, right, then it would also, since each quarter period is pi over 2, then this is going to be a quarter period right here. So we would have, in fact, hit this point right here at the origin, okay, and then on like that. Notice, though, might notice that this, in fact, is the sine wave, isn't it? If we had started this from right here and gone up to here and then down to here and then back to here, from 0 to 2 pi, that's exactly the sine wave as well, isn't it? From here to here, okay? We might notice that, in fact, the cosine of x minus pi over 2, which is the same as the cosine of pi over 2 minus x, because it was even, it turns out that that's exactly the same as just the sine of x. We can see graphically that those are exactly the same as each other. In other words, a horizontal shift by pi over 2 in the correct direction, right, of the cosine wave is going to give us the sine wave. Okay, so here's how we can use even and odd symmetry in order to simplify before we continue with our analysis. What would it look like if we did this with a sine function instead? So let's say we're given like f of x is equal to, how about negative 1 minus 5 times the sine of negative pi x plus pi. How about something like that? All right, lots of negatives floating around in there. So we have, in this case, k is equal to negative 1. That's our equilibrium. A right now is equal to negative 5. B is equal to negative pi. And C is equal to pi. Now, b is less than 0, and we want b to become greater than 0. So we're going to use the fact that sine is odd. Okay, we have sine is an odd function. An odd function, symbolically, we would have f of negative x is negative f of x. That is, the negative of the argument can move to the front to become a negative in front, right? A negative coefficient instead. So we have negative 1. Okay, first I'm going to want to factor out the negative 1 from the argument that we have here. So I have negative 1 minus 5 times the sine of negative 1 times pi x minus pi. So I factored out the negative 1 as the first step. Okay, just like we did with the cosine example a moment ago. Now, because this is an odd function, we can take this negative 1 right here and we can factor it out to right here. So it's going to multiply by the negative in front of the 5. Okay, so the function is rewritten as negative 1 plus 5 times the sine of, now the argument is pi x minus pi. Okay, and that describes the model after applying the odd symmetry. So here we have, let's see, the parameters are k is still equal to negative 1. Now notice that a, in fact, is equal to 5 instead of being negative 5. Because of the odd symmetry, that's what happened. Right? The sign of a actually flipped. B is now equal to pi instead of negative pi, so now it's positive. And c, which is the phase, c is equal to negative pi. Okay? And now we can go ahead and we can graph this. Right? We expect this wave, because it is a sine wave, where a is greater than 0, we expect one complete wave to graph from equilibrium up to the maximum and then around through the minimum back to equilibrium again. If we had graphed it using this information here, we would expect a sine wave that starts at equilibrium and goes down and returns like this. And again, remember that when you extend this outward in both directions, these are going to ultimately end up overlapping each other. It's where you start and complete one cycle, right, that's going to make the difference, okay, for really where you're labeling your quarter points. And that's also going to make a difference in what you determine as the actual horizontal shift as well, if you think about it. Okay, so this is the shape that we're going to have. Okay, where is the equilibrium? Equilibrium would be at negative 1. What is the maximum going to be? The maximum is at an amplitude of 5 north of negative 1, so 5 plus negative 1, well, that's equal to 4, right? Because the amplitude of the wave is equal to 5. And where's the minimum going to be? It would have to be an amplitude of 5 below negative 1, so it would have to be at negative 6, okay? And then you can go ahead and you can find the quarter points. All right, you can take the argument, which was pi x minus pi, and you can set it equal to the 5 quantities: 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, So we get pi x minus pi is equal to 0. Pi x minus pi is equal to pi over 2. Pi x minus pi is equal to pi. Pi x minus pi is equal to 3 pi over 2. And pi x minus pi is equal to 2 pi. Here are 5 linear equations for us to solve for x. The first one, add pi and then divide by pi, we get x is equal to 1. The next one, add pi, so we get pi x is equal to 3 pi over 2, and then divide by pi, well then x is equal to 3 halves or 1.5. The next one, add pi to get 2 pi, so pi x is equal to 2 pi, divide by pi, then x is equal to 2. Okay. The next one, add pi to 3 pi over 2, so we get pi x is equal to 5 pi over 2, divide by pi, then x is equal to 5 halves or 2.5. And then add pi to 2 pi, so we get pi x is equal to 3 pi, divide by pi, x is equal to 3. So we have the 5 quarter points are located at these 5 values. And h is going to equal 1 then. By the way, what's the period now going to be for the function? Okay, the period, well, I should take the period from here after we did the symmetry, where b is now a positive number. Okay, the period is equal to 2 pi divided by pi. That means the period is equal to 2. Just 2. Okay, no pi in there, right? Because b was equal to pi. So the period is equal to 2. Is that justified by our quarter points? Well, we're starting at x equals 1 and ending the cycle at x equals 3. So yes, the period is equal to 2. A quarter period then would equal a half. That is, these consecutive quarter points are each separated by a horizontal distance of 1/2. Okay, so we can plot these points on the curve. Let's see. Right, so for instance, I want to go as high as y is equal to 4 and as low as y is equal to -6. Okay, so 1, 2, 3, 4, and -1, -2, -3, -4, -5, and -6. And then this is -1 right here where we would find equilibrium. And the x values are going to be at 1, 1.5, 2, 2.5, and 3. So 1, let's do it this way. If I call this 1/2, and then this is 1, then this can be 3 halves, and this can be 2, and this can be 5 halves, and this can be 3, for example. And then I'll plot in green our points. This wave we expect to start at equilibrium and go up towards a maximum, and we can certainly check by plugging into the original function. So when x is equal to 1, we are at equilibrium, and equilibrium was -1. So I expect to start right here, 1, -1. Okay, and then we are moving up towards a maximum at the end of the first quarter period. That's when we get to 3 halves. We expect to be all the way up at the maximum already. That's up here at 4. Then when we get to x equals 2, right, we should be back at equilibrium again. So that would put us right back here. And then at x equals 5 halves, or 2.5, we expect to be at a minimum. So down here. And then at x equals 3, we're back at equilibrium again. So here we are. Okay, so it goes up like this. It curves around. Okay, it comes down here. And then back up again. Okay, and then we can repeat that cycle if we wish. All right, that would just continue indefinitely in both directions. Looks like after another 2 quarter periods, we'll be back here at -1 again. So I expect this is going to go down. This will go down all the way to a minimum and then back up again and cross through here at -1. Right, and then continue upward and so on and so forth, and it'll go off in that direction. All right, so we have our quarter point 1 right here. Here's quarter point 2. Here was quarter point 3. Here was our quarter point 4. And here was our quarter point 5. Okay. And we can check to see that this is going to be correct by plugging into the function, right? Like, for instance, what is f of 1 going to be? Okay, after we use the odd symmetry. Negative 1 plus 5 times the sine of pi x minus pi. So this would be negative 1 plus 5 times the sine of pi times 1 minus pi. Well, pi times 1 minus pi is equal to 0, so we get negative 1 plus 5 times the sine of 0, and sine of 0 is 0, so this is just equal to negative 1. Okay, let's take one more for good measure. How about 5 halves? F of 5 halves, well, that would be negative 1 plus 5 times the sine of 5 pi over 2 minus pi. That's negative 1 plus 5 times the sine of 5 pi over 2 minus pi is going to be 3 pi over 2. Going to the unit circle when t is equal to 3 pi over 2. The y coordinate is equal to negative 1, so the sine of 3 pi over 2 is negative 1. Negative 1 plus 5 times negative 1 is negative 1 minus 5 is equal to negative 6. So we expect a point on our wave at 5 halves, comma, negative 6, and that's exactly where we have quarter point 4 located. Okay, so it justifies the work that we did. Okay, so what's left to do in this section is let's take a look at a graph. Okay, at a graph and try to determine what is the function that would describe that graph that we're given. Determine an equation. An equation for the graph. Okay, and let's say it's either going to be in the form y equals k plus a times the sine of b times x minus h, or y equals k plus a times the cosine of b times x minus h. Okay, you could also put this in the form it's a times sine of bx plus c, or a times cosine bx plus c. But I'm just saying, let's write the instructions so we're trying to specifically find it in these forms. Let me construct a graph here that we'll try to figure out an equation for. If I take a graph that looks like maybe this, okay, and I'll put on the y-axis, I'll put that this is 5 right here, okay, and 4, 3, 2, 1. So I'll put that this is 2 right here. But I won't give the maximum. Alright. And then let's say 1. We'll put this at 2 and this at 3. And then this one can be at 4. Okay, and then 5 and 6. Try to do a little better job here. So it starts at 2. There's a minimum then at 3, 2. Okay, and then it comes back to an equilibrium at the point 4, 5. And then I have it going up towards a maximum, but I don't have the y value at the maximum noted. And then it returns back to an equilibrium again here, when x is equal to 6, for example. Okay. So given this picture, can we figure out what we have here? You know, what is k, a, b, and h? Can we figure out k, a, b, and h? And there really isn't only just there's really more than one possible combination that can work here. So let's look for maybe what is the most maybe the most appropriate combination based on the shape of our curve. And the shape of our curve, this wave, is like this. That seems to suggest a sine model because it starts at equilibrium and ends at equilibrium, and it seems to suggest that A is going to be less than 0 as well. Okay? Now the magnitude of A is equal to the amplitude. Right? Let's figure that out from the curve. The amplitude we can figure by taking the equilibrium value, which is 5, okay, and we can subtract from it the minimum, which is 2, right? That is equilibrium minus minimum, because we're given that information. Remember, if we had the maximum and the minimum, we could take the difference between the max and min and then divide that by 2. But here we're taking the amplitude by saying, well, what's the height rate here, for example, right? This from here to here, that would be the magnitude of A. That is the amplitude then. Okay, so the amplitude is equal to 3, it looks like in this case. But because of the shape of the sine wave, we want A to be negative. So the value of A that we select is negative 3. What's the value of K? Just from looking at the curve, we can tell directly the equilibrium happens to be K is equal to 5, and that's it. If we couldn't tell from looking at the curve so easily what the Y value was there, imagine if we knew the minimum and the maximum. We could take the average of those two, that is, add the max and min together and divide by 2, and that would have to be the equilibrium as well. What do we predict would be the maximum now? Right, the maximum would be found at equilibrium plus the amplitude, that is the absolute value of A. So plus 3, we predict the maximum would be located at 8 then, and the Y value of 8. How do you find B? Well, B is found, the frequency, by taking 2 pi and dividing by P, where P is the period. Can we find the period by looking at the graph? Well, that would be the length from the beginning of the cycle to the end of the cycle, from the beginning to the end of one complete cycle. And it looks like in this case the period is 6 minus 2, which is equal to 4. So if the period is equal to 4, then the value of B would be 2 pi over 4. Well, that is equal to pi over 2. So the value of B we should select would be pi over 2. What about the value of H? H is the x coordinate at quarter point 1. What's quarter point 1? Let's label it on the curve. Quarter point 1 is at 2, 5. So the value of H is that x value right there. So H is equal to 2. All right, I should be directing this from the correct model. We've selected the sine model. So the value of H, right, was equal to 2. Okay, so the model we're going to choose, okay, would be Y is equal to, first there's K, which is 5, plus A, but A is negative, so negative 3, okay? And we chose sine for the shape of this curve because it started and ended at equilibrium, times B, where B is equal to pi over 2, times the quantity x minus h, where h is 2, so x minus 2. Okay, and that's it. So there's our model. Note that we could expand this. Okay. We could expand this by distributing the pi over 2. We could get 5 minus 3 times the sine of, and then this would be pi over 2 times x minus pi. That would be in the form k plus a times the sine of the quantity bx plus c, where then c, the phase, which is c, would equal negative pi. Okay. But this is the answer right here. This is the answer in the form that we were asked to find. Okay. Now, if you're given maybe multiple waves, in some cases, right? Let's say you're given like a few waves, something like that, okay? And maybe you're told what the I'll go a little further. Right? Maybe you know what the x value is like here, Okay, maybe you're told the x value here is like negative pi over 3 or something like that. And then maybe you're not sure what any of these other x values are, right? Maybe until here or something like that. And maybe you're told there that the x value is like 5 pi over 4 or something like that. Okay, the question I have is, how do you figure out the period, therefore, and hence the frequency, okay, for a graph like this? Well, from here to here, these are the x values that we're given. Okay, how many complete cycles do we have? We have from here to here is one complete cycle, and then from here to here is another complete cycle. Okay, and then notice that from here to here we get a half of a cycle. So I have from here to here we have 2.5 periods, right? I notice I have 2.5 times the period. Okay, 1, 2.5. 2.5 periods is equal to the difference between 5 pi over 4 and negative pi over 3. So in that case, we can solve for the period then by solving this little linear equation right here. All right, so we have 2.5 times p, okay, is equal to, what is that, 5 pi over 4 plus pi over 3. Okay, so 2.5 or 5 halves, right? I could say 5 halves if I want to use a fraction. Okay, 5 halves p is equal to, common denominator here would be 12, right? So we have 15 pi over 12 plus 4 pi over 12, so I get a 19 pi over 12. All right, so some weird number here. Multiply by 2/5, so p is equal to 19 pi over 12 times 2 over 5. Okay, so, all right, 19 pi over 12 times 2 over 5. Okay, so the 2 cancels with 12, gives us a 6 down there. So I get this weird number, 19 pi over 30. So guess what? That would be the period then, 19 pi over 30. I counted the number of complete cycles over a horizontal displacement that we can figure by the given x-coordinates. What I did not do, I did not assume to know the values at this x value. I didn't, okay? I did not assume this x value right here, okay, or this x value right here. Okay, I choose x values that I know for sure and where I can count complete cycles, okay, as best as possible, in this case also a half cycle, and then set up a little equation to figure it out in order to determine the period. Recall then that the frequency can then be figured out by dividing 2 pi by the period, for example, ... and then you can continue onward from there. Okay, so that completes being able to analyze the graphs of sine and cosine waves by either using the equation to construct the graph or by looking at the graph and building the equation in a couple of different forms, as you might see in this section. Okay, so try out the homework. Let me know if you have any questions. Of course, seek out tutors as well if you have additional questions or you want extra assistance. Okay, and I'll talk to you soon. Take care.